Let's build the uncertainty principle from first principles. It's not confusion, it's a structural limit built into nature. Classically, you imagine exact position and exact momentum together. But at atomic scales, matter behaves like a wave. Electrons and photons have wave-like behavior, not just trajectories. This helps explain why electrons don't just collapse into the nucleus.
You can't outsmart it. No clever technique beats the bound for the same state in observables.
You can reduce delta X, but only by increasing delta P. Squeezing redistributes uncertainty. Precision measurements face quantum backaction, like radiation pressure noise. Entanglement can change conditional predictions, but not violate the principle. EPR highlighted correlations, yet each local outcome still obeys quantum limits. Entanglement doesn't send usable information faster than light. At heart, uncertainty comes from wave structure and Fourier trade-offs. The same fact appears mathematically as non-commuting operators. It's not just observer disturbance, and not just ignorance. Quantum probabilities come from amplitudes that interfere, not hidden certainty. If delta X became tiny, delta P would explode, raising kinetic energy. Wave packets, Fourier analysis, and commutators all point to the same bound. So you can know position well or momentum well, never both arbitrarily well. In daily life, the bound exists, but it's far too small to matter. The ground state forms where total energy is minimized. Orbitals are standing wave patterns, not little planets in orbits. Even the lowest energy has residual motion, zero-point fluctuations. A Gaussian wave packet can saturate the bound, the smallest possible product. There's also a time-energy relation, but it's subtler than xp. A short-lived state needs a broad energy spread, seen as Linewood. That's why unstable excited states produce broadened spectral lines. But confining an electron tightly forces momentum spread and kinetic energy. Make position narrower, and the needed range of wave numbers grows. Since momentum p equals ah times k, wider delta k means wider delta p. So decreasing delta x forces momentum uncertainty delta p to increase. Quantitatively, the product obeys delta x times delta p at least h/2. This isn't about bad instruments, it's about the quantum state itself. Uncertainty means the width of outcome distributions. A classic example is diffraction through a narrow slit. The slit forces position uncertainty roughly equal to the slit width. But the outgoing angles vary, meaning transverse momentum varies. Narrower slit produces a wider spread of momentum, exactly the trade-off. Up to factors, the scale is delta p about h divided by delta x. Heisenberg illustrated this with a microscope observing an electron. Long wavelength light gives poor position resolution but small recoil. Short wavelength improves position but increases momentum disturbance. Measurement backaction agrees with the deeper wave Fourier reason. Formally, quantum properties are operators acting on states. Position and momentum are observables represented by operators. In quantum mechanics, the order of applying them matters. For position and momentum, the commutator equals I times h. Non-commuting operators obey a general uncertainty inequality. A particle is often a localized wave packet. Insert x and p, and you get the Heisenberg bound immediately. HH sets the scale, why quantum effects dominate only at small action. For macroscopic objects, AH makes the minimum product extremely small. Its height encodes probability of where you might detect it.
Repeat the same experiment. Results form a spread, not one value. Momentum is tied to wavelength. Shorter wavelength means higher momentum.
A single pure wavelength gives precise momentum, but no position. To localize, you must combine many wavelengths together. That's a Fourier trade-off between spatial width and spectral width. And that's the uncertainty principle, built from first principles.